In problem 15, we're asked to add two fractions with a common denominator of x plus 3. So we get to use that common denominator of x plus 3, and then we have to add the numerators since it's an addition problem. So we have 5x plus 7 plus x plus 11. Some of you might want to write it with a 1x. I'm not sure. So now we have a certain amount over x plus 3. We're combining like terms. 5x plus 1x is 6x. 7 plus 11 is 18. So in a sense, we've accomplished the task. We've added two fractions and we got a fraction for an answer. This is a certain amount of x plus 3's, and this is another amount of x plus 3's in a sense, and so this is the total amount of those x plus 3's. However, we always have to check and see if things reduce. The way to reduce is factor the top and the bottom. The bottom is factored. The top has a greatest common factor of 6 that comes out. We can check this by distributing the 6 through, and we get 6x plus 18. And now the common binomial factor of x plus 3, one on the bottom, one on the top, cancels, and we find out that this is 6. This means everywhere these fractions are defined, they add up to 6. So specifically, if x is 1,002,300, then this all adds up to 6. If x is -7, this all adds up to 6. Whenever these fractions are defined, they add up to 6. So again, we're adding two fractions that have a common denominator given to us. So we're going to collect the numerators by addition, since it's an addition problem. If it was a subtraction problem, we would subtract the two numerators and put them all over that common denominator. 3 plus 7 is 10. Negative 2x plus negative 3x is minus 5x. So again, this seems like it would be the answer, but we've got to do some factoring to figure out if it's really the answer. So on the bottom, I have x minus 4 times x minus 2, because negative 4 times negative 2 is positive 8, and negative 4 plus negative 2 is negative 6. Now, I could factor out a 5 here, but I'm just going to do a trick, and I'm going to factor out a negative 5. Because I like the result. When I factor out a negative 5, I get a negative 2 here plus an x. And a negative 2 plus an x and an x minus a 2, those are exactly the same amount. You can rewrite this top part as x plus negative 2 or x minus 2. So these are exactly the same. They cancel to 1. And we have negative 5 over x minus 4. So wherever these fractions are defined, these two fractions always equal this one. So if you put in, for instance, just to pick a number, if you put in x equals 6 here and do all the calculations, you would get negative 5 over negative 10 or 1/2, because this equals this always. There are many, many good ways to find the least common multiple of a couple of numbers or a couple of expressions. And I'm going to show you one that's perhaps not the easiest, but it is the most useful for where we're heading. So here's the way I would like you to think of least common multiples, or their close relation, least common denominators. So it's a least common multiple if there are no fractions in the problem. It's a least common denominator if there are fractions in the problem. And the thing I would like you to do is do the prime factorization of each of the things that you're dealing with first. In this case, they're numbers. So 36, in case you've forgotten how to do prime factorization, breaks apart into a couple of 2's times a couple of 3's. And 15 breaks apart into 3 times 5. And so now I want you to think of having some fractions that have those denominators. And I want you to come up with one thing. In this case, it's a number, where if you put it here and separately put it here, it can cancel all these guys, it can cancel all these guys, and it's the smallest, slimmest thing that does that. So for instance, here it doesn't need any 2's, but here it needs a couple of 2's. So this thing has to have a couple of 2's in it. Here it needs 1 3, but here it needs 2 3's. So 2 3's is good enough. Here it needs a 5, here it doesn't need any 5's, so it needs a 5. I claim that this collection of pieces, a couple of 2's, a couple of 3's, and a 5, is enough parts to cancel all these in this denominator, and separately, a separate copy cancels all these. Now that's a little bit complicated to think about, I agree, but it is pretty easy to use where we're heading. So notice I'm saying these 3's cancel, these 2's cancel, and we've canceled the denominator. This 3 cancels this one, this 5 cancels this one, and we've canceled the denominator. That means this thing that is the smallest collection of parts that can cancel both denominators, that thing is the least common multiple or least common denominator, depending on how your problem's worded. And so that is 2 times 5 is 10, times 18 is 180. So here the least common multiple is 180. So we'll follow the same idea that we did in the last problem. We're going to factor each of these quantities completely. The 6 is 2 times 3. We have an x and we have a couple of z's. The 8 is 2 times 2 times 2. We have a couple of x's and a y. The 15 is 3 times 5. We've got 3 y's multiplied together and a z. Now we are trying to create one thing. In this case, it's an expression with numbers and variables. And when we put a copy of it here, and another copy of it here, and another copy of it here, it's the smallest collection of parts that can cancel all of these, and all of these, and all of these. So let's just start with 2's. How many 2's does it need to have? Here it doesn't need any. Here it needs 1. Here it needs 3. So it needs at least 3 of them. So I wrote down 3, ridiculously enough. It needs 3 2's. And how many 3's does it have? It needs 1 here, none here, 1 here. So it needs 1 in each of them. Notice 1 in each of them is good enough, because this 3 cancels this one, and this other copy, this 3 cancels this one. There's 3 copies of this one thing. 5's, it needs a 5 for this. Doesn't really need a 5 for any of the others, but our least common multiple or least common denominator has a 5 in it. Let's go for the variables. An x times an x, no x's, so it needs an x times an x. A y, here it needs a y, here it needs 3 y's multiplied together. So I'm going to just say y cubed. I don't want to have to write in 3 y's, I'm running out of room. So that takes care of the y's. Now we have z's, we need a couple of z's, so I'll do a z squared. So we're going to have 2 to the 3rd power, 3 2's, times a 3, times a 5, times an x squared, times a y cubed, times a z squared. That is the least common multiple, or if there were fractions in the original problem, the least common denominator. Some people teach this and view it as whichever of these has the most 2's, use that many. This one has the most 2's, it's 3 of them, we use that many. Whichever has the most 3's, use that many. Here, it's a tie. This one has a 3, this one has a 3, so it's 1 3, etc., etc., etc.